Hi, this is Chris. In this video, I'm going to present my implementation of the module to compute the reciprocal of a divisor using Newton's method. However, before presenting the module, you may recall that I left you with a study question in the last video. How would you implement a lookup table for binary 16 reciprocal values, which allows the programmer to control the rounding mode and avoids the need to use Newton's method? After rounding, our final result is going to be an 11-bit quotient. The most significant bit of the quotient will always be 1, so we only need to store the bottom 10 bits. As a reminder, my rounding module uses the rounding mode and 3-bit flags to control how a significand is rounded. In addition to the quotient, I need to compute the 3-bit flag's last kept bit is odd, deciding bit is 1, and remaining bits are non-zero. The flag last kept bit is odd is the least significant bit of the reciprocal before rounding, so this bit will be part of the 10-bit quotient in the table. We need 2 additional bits in the lookup table. These 2 additional bits represent the values deciding bit is 1 and remaining bits are non-zero. So each entry in the lookup table will require 12 bits. As you may recall, I used the following code to compute 8-bit quotients. After stripping off the leading 1 bit, the code created the 7-bit per entry table. To create the lookup table for the study question, I modified the code to compute a 13-bit quotient. You can see that I've added 5 zeros to the end of the dividend and changed the mask to strip off the leading 1 bit, leaving only 12 bits of the quotient. At this point, the code has computed the least significant 10 bits of the quotient, which includes last kept bit is odd plus the bit flag deciding bit is 1, and allocated space for remaining bits are non-zero. The code continues by computing the value's remainder. The code then ORs the quotient together with the bit value, indicating whether or not the remainder is non-zero. These 12-bit entries are formatted as 3-digit hexadecimal values and printed. Now on to prototyping the circuits for binary 32, binary 64, and binary 128 values. Remember that each iteration of Newton's method requires 2 multiplications and 1 subtraction. When prototyping the binary 16 circuit, I kept all of the significant bits for each of these operations, and only reduced precision when performing the rounding operation to get the final binary 16 result. I'm going to need 2 iterations of Newton's method for the binary 32 format. This means that there will be 4 multiplications. If I keep all of the significant bits for each of these multiplications, the reciprocal value before rounding will grow to be about 100 bits long. To compute a binary 64 reciprocal would require over 300 bits, and a binary 128 reciprocal would require about 900 bits. This isn't reasonable. After each iteration of Newton's method, I need to reduce the number of bits of precision before beginning the next iteration. I decided to truncate each x sub I value to n sig plus 2 bits before beginning the next iteration. Let's start with binary 32. The prototype code extracts the 10 most significant bits of the significand field. That is, the 10 most significant bits excluding the implied leading 1 bit. This 10-bit value is used to generate x sub 0, our initial 9-bit guess for the reciprocal of the significand. After multiplying x sub 0 with the 24-bit significand of d, we have a 33-bit product. This product has 31 bits to the right of the binary point. We subtract the product of d times x sub 0 from a 33-bit version of 2, which has 31 of its bits to the right of the binary point. We now multiply the difference by x sub 0 to get a 42-bit product. This product has 39 bits to the right of the binary point. We shift this product right to get back to having only n sig plus 1 bits to the right of the binary point. This is our value for x sub 1. We repeat the process to calculate x sub 2, but note that things are now different. Our x sub 0 value has 9 bits, 8 bits to the right of the binary point. The value x sub 1 has 25 bits, and 24 of those bits are to the right of the binary point. So when we multiply d by x sub 1, we now get a 49-bit product. 47 of these bits are to the right of the binary point. This iteration, we subtract the product from the value 2, which also needs to have 47 bits to the right of the binary point. After subtracting the product of d times x sub 1 from 2, we again multiply by x sub 1. This time we have a 71-bit product. This is the value we round to get our final 24-bit reciprocal. Let's go back to the fact that x sub 0 and x sub 1 have a different number of bits. When we compute the reciprocal of a binary 64 value, we'll find that again, x sub 0 has a different number of bits from x sub 1 and x sub 2. X sub 1 and x sub 2 will each be 54 bits, or nsig plus 2 bits wide. The code for prototyping the binary 128 reciprocal will have x sub 1, x sub 2, and x sub 3, which are 114 bits wide. Again, this is nsig plus 2. And will also be different from the number of bits needed for x sub 0. If the prototype code appends a string of nsig minus 0 bits to the x sub 0 value, then the number of bits in x sub 0 and the subsequent x sub I values would be the same, and the prototype code could use a loop to compute the reciprocal of the significand. So that's what I'm going to do. Now the code computes the ceiling of the log base 2 of nsig plus 1. That is, the Python prototype code emulates the behavior of the SystemVerilog function $clog2. The Python code then uses the clog2 value to control how many iterations of Newton's method need to be performed for the binary 32 floating point format. The benefit of using a loop for each iteration of Newton's method will carry over from the prototype code into the Verilog version of the circuit. Now that I've prototyped the circuit in Python, I'm ready to implement the circuit in SystemVerilog rather than Verilog. For the same reason I use SystemVerilog for the FP class module. SystemVerilog has the $clog2 function. The structure of the state machine is similar to the division state machine presented in part 2 of the division videos. On the positive edge of each clock signal, the module looks to see if the start signal is asserted. When the start signal is asserted, the module determines if the divisor value is a special case. We have a special case if the divisor is a signaling NaN, a quiet NaN, an infinity, or 0. If the divisor is a normal or subnormal number, the module generates the initial guess for the significand and the exponent of the reciprocal x sub 0, and sets a counter which the state machine uses to determine when the reciprocal of the divisor has been successfully computed. The module also sets a state variable to keep track of which Newton's method operation is to take place on the next clock cycle. For the next clog2 nsig minus 3 times 3 clock cycles, the module performs clog2 nsig minus 3 iterations of Newton's method. Remember that each iteration of Newton's method requires 2 multiplications and 1 subtraction. By using the state variable, the module keeps track of which of these 3 operations to perform next. Also note that during the last iteration of Newton's method, the module sets the state variable to round. The code doesn't really need to do this, but I thought it was appropriate for completeness. The value of the counter variable controls whether or not the module performs another iteration of Newton's method, not the state variable. During the next clock cycle, after the final iteration of Newton's method, the module performs rounding. The remainder of the logic for the reciprocal module is very much like the state machine covered in part 2 of the series on division. If you need a refresher, there should be a link on your screen now which will take you to the earlier video. There are problems with the module. I would encourage you to examine the module to see where you think improvements can be made. Before wrapping up the video, I do want to make a few comments about my implementation of the X0 module, that is, the module which generates the initial guess for the Newton's method iterations. The code I've written is much longer than the code which Chris Fenton has written for his Reciprocal module. And it's not just because my lookup table has 1024 entries versus the 128 entries in Mr. Fenton's table, though that does play a part. As I mentioned in my introduction to this series, I'm a Verilog newbie. Before writing the X0 module, I had never written my own Verilog primitives, so I took the opportunity to do so when writing the X0 module. My lookup table code constructs the X sub 0 value from a table with 7-bit entries. Each bit of each entry has its own primitive module. Each primitive module has a 1024 entry table. At the top level is a wrapper module which assembles the 7 individual bits into a 9-bit result. I didn't generate the X0 code by hand. I used a Python script. This script, make recip_lut, is also in the GitHub repository for this video. If you run the Python script and generate a new copy of the file x0.v, you'll find that the Python script output doesn't match the code which is currently in the GitHub repository. The differences are caused by changing the size of the return value from being 9 bits wide to being nsig plus 2 bits wide. As I stated earlier, when discussing the Python prototype code, padding out the lookup value facilitates using a loop to avoid code redundancy in both the Python prototype code and the System Verilog module. Maybe it's wishful thinking on my part, but I expect that the Verilog compiler does a good job optimizing the tables when mapping out the FPGA implementation. At some point, I want to see if I can use Quine-McCluskey minimization and reduce the tables to logic statements. This video has 2 GitHub repositories. The first is for the Python prototype code. The second is for the System Verilog module. Included in the GitHub repository for the reciprocal module is a test bench which computes binary 16, binary 32, binary 64, and binary 128 reciprocals. When you examine these 2 repositories, you'll find that they have more history showing the evolution of the code than previous code repositories for this video series. You may or may not find this additional history useful. Remember that the location for the code discussed in this video can be found in the comments section. In the next video, I'm moving on to a slightly different approach to performing floating point division. Please share this video with friends and colleagues who might have an interest in this series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.